Welcome back to the Deep Dive. Today we're taking a stack of sources that span, well, nearly every scientific discipline you can imagine.
It's quite a pile. We've got pure number theory, map making, planetary mechanics,
Electromagnetism. And we're using all of it to try and understand a single colossal figure.
a person whose influence is so pervasive
Yeah.
that, the unit of magnetic flux density is named the gas.
Right. And something like over 100 concepts in math and science still bear his name. We are, of course, talking about Carl Friedrich Gauss.
Indeed. Gauss, born in 1777, is universally acknowledged as the Prince of Mathematicians.
But I think the sheer breadth of the sources we have today proves that title is, well, it's actually too limiting, isn't it?
It is. He was equally a prince of astronomy, a prince of statistics, and a prince of geodesy, the science of measuring the Earth.
That's right. I mean, our listener has gathered materials detailing his work in number theory, algebra, geometry. It just goes on and on. It's overwhelming just looking at the table of contents of his collected works.
So to cut through that density, we need a specific place to start, a hook, something that really shows the kind of genius we're dealing with. And for me, that starts with an unbelievable fact.
Okay, let's unpack this. Give us the moment that changed everything for him.
The year is 1796. Gauss is 19 years old, studying at the University of Göttingen. He's already shown, incredible talent, but he's torn.
Torn between what?
Between pursuing classical philology, so the study of language and literature, and mathematics, then he decides to tackle a geometric construction problem.
And not just any problem.
No, a problem that had remained unsolved since the age of ancient Greece, constructing regular polygons using only a compass and a straight edge.
That's the classic limitation geometry students still deal with today.
Yeah.
You can easily construct an equilateral triangle or a square, a regular pentagon, but for 2 millennia, certain other numbers of sides, like a 7-sided septagon, seemed impossible. It was this foundational, unsolved riddle.
And Gauss provides the solution. He proved, unequivocally, the constructability of the regular heptadecagon.
The 17-sided polygon.
Exactly. And this wasn't just him solving a tough math problem. This was the first major new discovery in regular polygon construction in over 2,000 years.
Right, how did he even do that? How do you take a geometric challenge like drawing a shape with 17 sides and turn it into something solvable? That connection, that leap, seems like the real revolutionary breakthrough.
That is the core insight. Our sources confirm that Gauss reduced the problem of constructibility to an algebraic one.
So he translated the picture into numbers.
Precisely. He showed that a regular n-gon is constructible if and only if the number of sides, n, is a power of 2 multiplied by a product of distinct Fermat primes.
Which are primes in the form of 2 to the power of 2 to the k plus 1.
Exactly. And 17 just happens to be one of those Fermat primes. By connecting geometry to the algebra of what are called cyclotomic fields, he just cracked the problem wide open.
And that, our sources say, solidified his decision. Math it is. Philology is out.
That's the story. An incredible origin for a career.
So for you, the listener, our mission today is to move beyond these high-level titles and really unpack the depth of his influence. We need to see how his almost fanatical devotion to fundamental mathematical rigor, the certainty he demanded in all his proofs, was directly applied to solve the most pressing, practical, and even celestial problems of his time.
We're looking for those surprising connections. How does the man who codifies number theory also somehow redefine map-making? We need to look at the nuggets that demonstrate why his influence is so deep and so wide.
To the point where we have to realize that every time we discuss modern statistics or electromagnetism or even digital signal processing, we are in some way building on a foundation that Gauss laid.
It's all a Gaussian foundation.
It's important to remember, though, that his success was anything but inevitable. If we look at the foundations, he did not come from a family that promised intellectual greatness.
Absolutely not. He was born in Brunswick in 1777, and his social status was decidedly low. His father, Gebhard Dietrich Gauss, was a hard-working, but according to the accounts we have, a rough and dominating man.
He did all sorts of jobs. Right?
All sorts. A butcher, a bricklayer, a gardener, sometimes a minor fund treasurer. His mother, Dorothea, was almost entirely illiterate.
So he didn't have that inherited privilege or the formal early schooling we often associate with the great geniuses of that era. How did he break out of those circumstances?
Well, his talents were just too large to ignore, even in an elementary school classroom. Early teachers noticed his abilities, and this led to the crucial intervention.
The patronage.
The patronage of the Duke of Brunswick, Charles William Ferdinand. The Duke stepped in and provided the financial support that made his education possible, funding his studies at the local Collegium Carolinum and later at the University of Göttingen.
Without that, it's hard to imagine how his raw talent could have been cultivated into such a formidable intellect.
It's almost impossible to imagine.
And the anecdote we all hear about that early stage, it just perfectly encapsulates the difference in how his mind processed information, the legendary summation problem.
That story is absolutely foundational to understanding him. The elementary school teacher, a man named J.G. Büttner, wanted to keep the class busy.
Give him some busy work.
Right. So he tasked the students with summing all the integers from 1 to 100. It was tedious, rote labor, designed to take a very long time.
And what happened?
Gauss places his slate down almost instantly with the correct answer on it, 5,050.
How?
He hadn't added them sequentially, 1 plus 2 plus 3, and so on. He saw the pattern. He realized if you pair the first number with the last, 1 plus 100 is 101.
And the second, with the second to last, 2 plus 99 is also 101.
You keep going. You get 50 pairs, and each of them sums to 101. So the total sum is simply 50 multiplied by 101.
It wasn't about speed. It was about restructuring the problem. He didn't just calculate. He found the algorithm, the underlying rule that made the calculation trivial.
That's precisely his genius. It's this fusion of empirical calculation, pattern recognition, and incredible speed. He always sought the most elegant and structurally correct way to solve a problem. And this intellectual drive led directly to his first great publication.
Disquisitiones Arithmeticae, published in 1801. He was only 24.
And this book is monumental because it took number theory, which at the time was often just a collection of, disparate observations and theorems.
A bit of a mess.
A bit of a mess. And he consolidated it into a formal, structured, modern discipline.
He really standardized the field.
He did. And one of his most fundamental contributions in that work was the formal introduction of modular arithmetic. Before Gauss, mathematicians talked about remainders in these really clumsy ways. Gauss introduced the notation we use every single day, the triple bar symbol for congruence.
That one symbol, which seems so basic now, gave everyone a concise language to talk about remainders and cycles cleanly. It's essential for everything from basic algebra to modern cryptography.
Exactly. And beyond the notation, Disquisitiones Arithmeticae tackled two major lingering problems. First, it contained the definitive proofs for the law of quadratic reciprocity.
Okay, that's a mouthful. What is that?
It's a theorem that connects the solvability of two related quadratic congruences. It had been partially explored by giants like Fermat, Euler, and Legendre, but Gauss delivered the first definitive, comprehensive proofs.
He was pretty proud of it, I hear.
He was so proud of it, he named it the Theorema Aureum, the Golden Theorem.
And this wasn't just abstract work.
Not at all. He also proved the triangular case of Fermat's polygonal number theorem, which showed that every integer can be represented as the sum of three triangular numbers.
And tying back to our opening anecdote.
He did. The final section of Disquisitiones contained the full theory explaining which regular n-gons are constructible, linking that geometric problem all the way back to the algebraic structures inherent in number theory.
So we're seeing the foundation being laid here, not just of brilliance, but of a new standard for mathematical presentation and proof.
This is critical to understanding his broader legacy. For instance, Gauss achieved the second and third complete proofs of the fundamental theorem of algebra,
which is essential for understanding the concept of complex numbers.
It's the theorem that states every non-constant polynomial with complex coefficients has at least one complex root. Earlier attempts to prove this, famously by D'Alembert, had gaps in them. Gauss's 1849 proof is the one generally considered fully rigorous.
And this commitment to rigor defined his whole style. Our sources suggest that his approach contrasted heavily with predecessors like Euler, who sometimes, revealed their entire exploratory thought process. You could see the dead ends and all.
Right. Gauss introduced a revolutionary, almost severe style of exposition. He only published work when he deemed it absolutely complete and beyond reproach. He deliberately scrubbed away the signs of his rough work, his journey of discovery.
And this commitment to perfection was summed up in his personal seal motto.
Poca sed matura. Few, but ripe.
That's a powerful statement. He wasn't just trying to publish first. He was trying to publish perfectly.
And the mathematician Felix Klein noted that Gauss successfully restored that high rigor of demonstration admired in the ancient Greek masters, ensuring that every subsequent mathematical step was built on rock-solid certainty.
This standard of mathematical certainty, this quest for the elegant, final, undeniable proof, is what guided him throughout his career, and it's what pushed him to demand the same level of certainty in the messy, inexact world of physical observation.
Now, we move from the certainty of pure number theory to the inherent uncertainties of the physical world. And the rigor Gauss established in his early career proved absolutely essential when he was faced with one of the most dramatic scientific challenges of the early 19th century.
A missing planet.
This is the story of Ceres. It was an astronomical crisis that turned Gauss into a world celebrity. On January 1st, 1801, the Italian astronomer Giuseppe Piazzi discovered a new celestial object.
And everyone thought it was the long-sought planet between Mars and Jupiter.
Exactly. He named it Ceres. But the problem was, the observations were limited to a very short arc of time before Ceres passed too close to the sun's glare and just disappeared.
So when it was expected to reappear, nobody could predict where to look.
The problem was acute. Contemporary methods required a long, comprehensive series of observations to reliably calculate a full orbit. Given the limited data Piazzi had recorded, the existing mathematical tools were just insufficient to predict its reemergence.
The astronomical community feared Ceres was lost forever.
It really did. And Gauss, using his unique talents for pattern recognition and massive calculation, stepped in.
So what did he do differently?
He tackled the problem by developing entirely new, comprehensive approximation methods. Instead of trying to find the perfect equation instantly, he recognized that the limited data needed to be treated using error minimization techniques.
Which we'll get to.
Which we will get to. He had to solve an eighth-degree equation to define the orbital parameters, which involved these incredibly complex iterative calculations, all by hand, but refined by his new methods.
An eighth-degree equation by hand to find a lost planet based on a few data points. That is a stunning mathematical feat for 1801.
It was. And his prediction was revolutionary. When astronomers Franz Xaver von Zach and Heinrich Olbers searched the predicted position in late 1801 and early 1802, they found Ceres.
Right where he said it would be.
Near the exact location Gauss had calculated, accurate within less than half a degree. His success was celebrated all across Europe.
And that success led directly to his magnum opus on celestial mechanics.
That's right. Theoria Modus Corporum Coelestium theory of the motion of heavenly bodies, published in 1809. This work introduced the foundational theory of orbital mechanics for objects disturbed by large planets. It's still used for calculating asteroid and comet orbits.
And it also introduced the Gaussian gravitational constant, which standardized planetary calculations.
And this triumph secured his position as director of the Göttingen Observatory in 1807, a role he would maintain for the rest of his life.
So, he masters the cosmos, but his day-to-day life revolved around the ground beneath his feet. This brings us to geodesy and the immense survey of Hanover.
Yes, from about 1820 until 1844, Gauss was tasked with leading the triangulation survey of the Kingdom of Hanover. This wasn't just a fun project for him. It was essential practical work.
For creating accurate property lines, tax records, administrative maps.
Exactly. The sheer scale was massive, involving high-precision measurements across hundreds of miles of diverse terrain. And this required the highest possible measurement standards, often over long, challenging sightlines.
Which is why he had to innovate.
Right, the existing instruments were inadequate. So in 1821, he invented the heliotrope.
Which means sun-turner.
Sun-turner. It was an instrument using movable mirrors and a small telescope to reflect concentrated sunbeams across vast distances, often dozens of miles, allowing surveyors to sight triangulation points with phenomenal accuracy. He even developed a smaller version, the Weiss heliotrope, to ensure redundancy and precision.
This highlights that core aspect of his genius. When the mathematical tools or the physical instruments didn't meet his standards of certainty, he just invented better ones.
And the theoretical output from this was as important as the practical maps. His geodetic work required a system for dealing with the Earth's shape. So he developed the universal transverse Mercator projection, what he called his conform projection.
And that provided a systematic way to flatten the Earth's ellipsoidal surface onto a plane chart with minimized local distortion.
And his attempt to formalize the Earth's actual shape resulted in a concept we still use today. In 1828, he formalized the definition of the Earth's physical figure as the surface everywhere perpendicular to the direction of gravity.
Which essentially means sea level, but extended globally.
Right. And this shape, defined by gravity, was later named the geoid by his student Johann Benedict listing.
Okay, here's where it gets really interesting, because the demands of this practical work plotting series and mapping Hanover forced him to confront the inescapable reality of measurement error.
And that is the foundation of modern statistics. Gauss pioneered the methodology necessary to deal with these inevitable observational errors, the method of least squares.
The cornerstone of statistical regression today.
It was absolutely essential for minimizing the impact of noise in both astronomical predictions and geodetic triangulation. The method works by finding the curve or line that minimizes the sum of the squares of the differences between the observed data points and the curve itself.
But this leads to a significant historical conflict, a priority dispute.
The famous priority dispute. Adrien Marie Legendre published the method of least squares in 1805. However, Gauss claimed in his Theoria Modus in 1809 that he had been using this same method since as early as 1794 or 1795.
Now, Gauss was notoriously secretive, adhering to his pauca sed matura rule. So how did he justify claiming priority over someone who actually published it first?
He provided the theoretical justification for the method's superiority. While Legendre provided the method as a useful calculation tool, Gauss later published a whole work, Theoria Combinationis, in 1823, which proved the method's optimality.
So he didn't just use it, he proved why it was the best.
Exactly. This is the famous Gauss-Markov theorem, which states that under the assumption of normally distributed errors, which is often the case for measurement errors, the method of least squares provides a linear, unbiased estimator with the lowest sampling variance.
So he moved the method from a useful empirical trick to a rigorously proven mathematical necessity.
And for Gauss, priority lay not just in calculation, but in the complete, rigorous theoretical mastery of the subject.
That is peak Gauss. He didn't just get the right answer. He dedicated years to proving why the method used to get the answer was fundamentally superior to every other method. This obsession with certainty, even in the face of random error, is what defined his contribution to the modern scientific method.
And it's important to remember that the practical work of mapping the Earth's surface, that immense geodetic survey we just discussed, was the direct inspiration for some of his deepest theoretical insights into geometry itself.
So the messy, physical Earth leading to the purest abstract math.
It's a perfect example of his interdisciplinary mind. It took him into the realm of differential geometry, which deals with the curves and surfaces of the Earth. In 1828, he published his General Investigations of Curved Surfaces, essentially creating modern differential geometry.
And the crowning achievement of this work is the Theorema Egregium, the remarkable theorem.
This theorem is just conceptually beautiful. It states that the Gaussian curvature of a surface, which is the intrinsic measurement of how much it deviates from being flat, can be determined purely by measuring angles and distances on the surface itself.
So you don't have to look outside the surface into three-dimensional space.
You don't.
I think we need an analogy to fully grasp that. How can a surface know its own curvature?
Okay, imagine you're an ant living on a massive crumpled piece of paper. If the paper has a Gaussian curvature of 0, like a cylinder or a flat plane, you can measure distances and angles, and you will find that the rules of Euclidean geometry hold true. The angles in a triangle add up to 180 degrees. However, if you, the ant, are living on a sphere, the angles of a large triangle will sum to more than 180 degrees. The Theorema Egregium proves that you, the ant, can perform these measurements and discover this fact without ever needing to know that your surface is sitting inside a larger 3D space.
That's fascinating, and this is why every world map is a lie, right?
Precisely. The theorem proves why you cannot flatten a sphere into a plane without massive distortion. A sphere has non-zero curvature. A plane has zero curvature. An isometric or distance-preserving transformation between surfaces of different curvature is impossible. That is the fundamental problem of map projection.
Now we need to circle back to the biggest what-if of his career, a discovery driven by this new geometric insight that he chose to keep entirely secret, non-Euclidean geometry.
This is one of the most frustrating aspects of the Pauca-Sed-Matura principle. For over 2 millennia, Euclidean geometry, based on 5 foundational postulates, was held as absolute truth.
And Gauss started thinking about the parallel postulate.
Right. The idea that through a point not on a given line, only one parallel line can be drawn. Sometime in the 1810s, he realized that a perfectly consistent geometrical system could exist without it. He even coined the term non-Euclidean geometry.
So if he made this discovery, why was he silent? Why not publish?
It boils down to his profound conservatism and his fear of controversy. Acknowledging that geometry could be non-Euclidean was a radical philosophical break that challenged foundational truths held since antiquity.
And he didn't want the pushback.
He didn't. We know from his private correspondence, like a letter to Franz Torinus in 1824, that Gauss had worked out the details, but explicitly advised Torinus to keep the idea private, believing the public was just not ready for such a challenging concept.
So because of his secrecy, the first public publications of non-Euclidean geometry belonged to Nikolai Lobachevsky in 1829 and János Bolyai in 1832.
Correct. And when he received Bolyai's work, he was complimentary, but he also famously claimed that he couldn't praise it because, as he put it, to praise it would be to praise myself, since the whole content of the work coincides almost entirely with my own meditations, which have occupied my mind for the past 30 or 25 years.
Ouch. That must have been devastating for Bolyai, a young mathematician seeking validation.
It was certainly a contentious claim, but the depth of his private notebooks, which were published posthumously, revealed that he truly had developed the concept extensively. His refusal to publish delayed the mainstream acceptance of this concept for decades, a massive opportunity cost for science.
Let's shift gears completely now and look at his profound impact on the realm of physics, specifically electromagnetism and magnetism.
Yeah.
And that started with a collaboration.
It did. This was driven by his partnership with the physicist Wilhelm Weber, who arrived at Göttingen in 1831, and their association with the naturalist Alexander von Humboldt. They focused intensely on geomagnetism, studying the Earth's magnetic field.
And this collaboration led to the founding of the International Magnetic Association between 1836 and 1841.
It sounds dry, but this was the beginning of large-scale, international standardized science. It was pioneering and highly influential.
What was the problem they were trying to solve?
They recognized that magnetic measurements were inconsistent globally, so the association standardized measurement methods worldwide, demanding that magnetic readings be taken under equivalent conditions at prearranged dates, often 12 times a year, across 61 stations on 5 continents.
And they even used Göttingen mean time as the standardized clock.
They did. This effort to coordinate scientific data collection globally was revolutionary. It was known enthusiastically as the Magnetical Crusade.
And the instruments they developed were critical to making these standardized global measurements possible.
Absolutely. In 1833, Gauss and Weber constructed a sensitive magnetometer. Crucially, this instrument was designed to measure the absolute values of Earth's magnetic field strength. Previously, measurements were only relative to the apparatus being used.
But Gauss was the first to show how to derive a non-mechanical quantity, like magnetism, using only fundamental mechanical units, mass, length, and time.
Right, effectively creating the first true, absolute system of electromagnetic measurement.
And his mathematical analysis of that global data set.
He applied his advanced technique of spherical harmonic analysis, the one he developed for the geoid, to the magnetic data.
Yeah.
Spherical harmonic analysis is essentially the process of breaking down a complex, bumpy, or asymmetrical distribution,
Like the Earth's magnetic field,
into simpler underlying wave patterns. By doing this, he was able to prove that the vast majority, about 95% of Earth's magnetic field, originates from internal sources within the planet, rather than external sources like the sun.
That collaboration also briefly ushered in the electric age right there in Göttingen, didn't it?
It did. In 1833, Gauss and Weber constructed the first functional electromagnetic telegraph. They strung a wire connecting the Göttingen Observatory, where Gauss lived, to the Physics Institute in the town center. And they used an early form of binary code to transmit messages instantly.
So they invented a working telegraph, demonstrating the concept beautifully, but once again, they never commercialized it.
It fits his pattern perfectly. He achieved the scientific breakthrough, but the rigorous preparation for commercializations or mass publication just didn't appeal to him as much as the pure problem-solving itself.
And he had bigger fish to fry, theoretically.
He did. Later in his theoretical work, Gauss attempted to find a single, grand, unifying law for long-distance effects across electrostatics, electrodynamics, and induction. He was hoping for something with the same explanatory power as Newton's law of gravitation. He never fully achieved that unification.
But once again, his private notebooks reveal hidden discoveries that others were credited with later.
Indeed. His papers show independent, unpublished discoveries like the vector potential function and an induction law equivalent to Faraday's law written down in 1835. It is just staggering how much foundational work he completed across all these fields, often without bothering to publish or claim credit.
That raises a question, though. Was his relentless rigor always a good thing, or did his perfectionism make his work impenetrable to his contemporaries, even when he did publish?
That's a critical point. While his style was meticulous, it was often too condensed and too rigorous for the average scientist of the day. His work required deep dedication to follow, which sometimes masked the sheer scope of his findings. He published the results but often hid the insights and the exploratory paths that made the results meaningful to others.
He was everywhere, wasn't he? We haven't even touched on his work on the arithmetic geometric mean or hypergeometric functions or Gaussian quadrature.
Well, his influence on computational mathematics is profound. Take Gaussian quadrature. This is a highly efficient numerical method for approximating integrals, which is essential for almost all scientific computation today. It replaces a messy integration calculation with a simple weighted sum, dramatically speeding up complex numerical analysis.
And his development of this and other tools proved he wasn't just a theoretician.
Not at all. He was a master of computation, always seeking efficiency and certainty.
So let's delve deeper into the man himself. Returning to his personal creed, Pauca said matura, few, but ripe. What was the ultimate cost of this perfectionist's creed on the global scientific community?
It meant that the pleasure for him was in the internal act of learning and mastering the subject, not the external act of possessing or proclaiming knowledge. The effort required to prepare a presentable, complete elaboration was the demanding part, and if he didn't feel it was perfect, it stayed in his desk drawer.
And the most famous example of this cost us over a century of technological development.
Yes, the fast Fourier transform. In 1805, Gauss developed an algorithm for calculating discrete Fourier transforms. He did this specifically to handle the astronomical calculations for the orbits of newly discovered asteroids Pallas and Juno. This was functionally an early version of what we now call the fast Fourier transform, or FFT.
The FFT is arguably the single most important algorithm in digital technology today. I mean, everything from Wi-Fi and audio compression, like MP3s, to medical imaging, like MRIs and cell phone technology, relies on the FFT's ability to quickly break down complex signals into their component frequencies.
And yet his paper on it, Theoria Interpolationis Methodo Nova Tractata, was only published posthumously in 1876. This was a staggering 160 years before James Cooley and John Tukey published their similar, widely adopted algorithm in 1965.
So if the FFT had been published in 1805, I mean, imagine the head start that would have given digital processing, communication technology, computer science. We might have seen cellular technology 50 or 60 years earlier. It's an enormous opportunity cost.
It truly illustrates the profound impact of his secrecy. His contemporaries frequently urged him to publish more, knowing the breadth of his work, but his belief in priority belonged to the discoverer, not the publisher, allowing him to justify his silence.
Which ties into his controversial stance on priority. He accepted the title Prince of Mathematicians, but he often seemed dismissive of others' claims.
He certainly held a contentious view. Regarding the least squares dispute, he believed that since he had discovered and used the method first, he deserved credit, even if Legendre was the first to share it with the world. He also often criticized other citation practices while simultaneously being negligent in citing his own sources.
Claiming that proper citation would require a vast historical effort he was unwilling to undertake.
Exactly.
Beyond his scholarship, what do we know about the private man? Our sources suggest he was often difficult.
His life was shadowed by significant personal hardship. He was married twice. His first wife, Johanna, died tragically young in 1809, shortly after the birth of their son Louis, who himself died a few months later. Gauss was utterly devastated, and his grief is apparent in his private letters.
And his second wife?
His second wife, Minna, suffered from a debilitating decade-long illness until her death in 1831. These tragedies undoubtedly compounded his naturally reserved and somewhat difficult personality.
And what about his reputation as a teacher?
He had a distinct aversion to teaching. He found the act of lecturing a burden, a waste of time he could have spent on research. He disliked the superficiality and the need to explain things that, to him, were obvious.
But despite his reluctance, his students included titans who would shape the future of math.
They did.
They did.
Notably, Richard Dedekind and Bernhard Weyman. So his genius found a way to influence the next generation despite his pedagogical reluctance.
And what became of his own children? I understand 2 of them fled to the United States.
Yes. 2 of his sons, Eugen and Wilhelm, emigrated. Eugen, who was described as having a lively and sometimes rebellious character, ran up substantial debts and caused a family scandal, forcing him to leave Göttingen suddenly in 1830.
And he ended up in the U.S. Army.
He did. He served 5 years before becoming a highly successful businessman in Missouri. Wilhelm also moved to Missouri, initially farming, but eventually making a fortune in the shoe business in St. Louis. Only his youngest daughter, Therese, stayed in Göttingen to care for him until his death.
And we have to mention the bizarre, almost ironic twist involving his physical remains.
You're referring to the story of his brain.
It seems like a cruel joke on the ultimate seeker of certainty.
The irony is astounding. After Gauss died in 1855, his brain was removed and preserved for study, given the massive scientific interest in his unique intellectual abilities. It was measured at 1,492 grams, slightly above average. However, for decades, it was mixed up.
What happened?
Due to mislabeling shortly after the initial investigations, Gauss's brain was accidentally switched with the brain of a contemporary physician, Conrad Heinrich Fuchs, who had died just a few months after Gauss.
Wait, you mean for over 150 years, neurobiologists and scientists were studying and publishing on the brain of the wrong man?
That's exactly right. The scientific investigation into the physical source of his genius, analyzing the gyri and sulci of his cortex, were based entirely on the physician's brain. It wasn't until 2013 that neurobiologists conducted DNA analysis and confirmed the mix-up.
Long after the initial studies had been widely circulated.
It's an almost perfect, dark, comedic ending to a life dedicated to eliminating error.
What do we know about his intellectual tastes outside of the hard sciences?
He maintained a broad curiosity throughout his life. He was a constant reader of newspapers and loved literature, particularly the works of Sir Walter Scott in English and Jean-Paul in German.
And in a testament to his sheer lifelong curiosity, at the age of 62, he decided to teach himself Russian.
He did. Likely in part to read the scientific writings of others, including those of Lobachevsky, on the very geometry he himself refused to publish.
And he remained skeptical of pure philosophy, viewing the work of metaphysicians as splitting hairs.
His focus remained strictly empirical and rigorous. He died in Göttingen in 1855, and fittingly, shortly after his death, King George V of Hanover issued a commemorative medal dedicated to the Prince of Mathematicians.
So, what does this all mean for us today? For the learner trying to synthesize this mountain of information, we've seen that Carl Friedrich Gauss was instrumental in the birth of modern number theory. He revolutionized geodesy, he created differential geometry, he co-pioneered the telegraph, and he established the rigorous standard for statistical error minimization.
His career proves that true genius operates across boundaries. He used fundamental mathematical certainty, the rigor he instilled in his proofs, to solve the most pressing practical and celestial problems of his time. He didn't just solve existing puzzles. He created the advanced language, the tools, and the methods.
From least squares to the FFT?
That his successors would rely on for centuries. The fact that over 100 concepts bear his name is the most immediate proof of his singular importance.
But his legacy also includes that vast trove of unpublished material, the Pauca Matura?
And it leads us to a final provocative thought for you to consider. If Gauss prioritized the internal act of learning over the external act of possession of knowledge, causing him to delay or bury discoveries like non-Euclidean geometry and the fast Fourier transform, discoveries crucial to the modern world that were eventually remade decades later.
And then how much knowledge, how many critical applications, or even entire industries might have been delayed by decades or centuries because Gauss, the ultimate perfectionist, chose silence over rapid dissemination.
What might we be missing right now, today, that is currently ripe, as he would say, but remains unwritten and unpublished, waiting for the next generation to rediscover simply because the original discoverer, in their quest for personal certainty, judged it not mature enough to share?
It makes you wonder about the responsibility of genius in our increasingly connected age. A profound question to mull over. On that note, thank you for diving deep into the extraordinary legacy of Carl Friedrich Gauss. We'll see you next time.